we have been discussing few elementary concepts of linear algebra in last few classes. We have discussed about linear independence, spanning, basis, dimension, these definitions, and then we also discussed about fundamental subspaces related with a matrix A in the context of solving Ax is equal to b equation, and these spaces are row space, column space, null space and left null space. We will continue the same discussion and we will try to look more from the perspective of solution of X is equal to b, and using the definitions of these spaces, if we can build our understanding more sound on solvability of X is equal to b, whether solutions exist and when the solutions are when there is a unique solution of X is equal to b. So, we will look into the perspectives in more detail using the basic understandings of linear algebra which we have developed over last few classes. So, today's discussion is on left inverse, right inverse and the fundamental subspaces. The important part which we will recapitulate in this discussion before starting this discussion is the theorem which says row rank is equal to column rank, and that implies that number of independent columns in a matrix is equal to number of independent rows. And this can, if we can remember, this has been shown by considering the echelon form or reduced to echelon form of a matrix, the R form R of a matrix A, where we got the pivoted rows, and number of pivoted rows is same as number of pivoted columns, and these are the independent rows and independent columns of matrix A when transformed into reduced to echelon form. Therefore, the number of independent rows and number of independent columns is exactly same as the number of pivots in the reduced to echelon form. So, these numbers are same. Therefore, number of independent columns and number of independent rows same implies that dimension of the row space and dimension of the column space is same, or row rank of the matrix or column rank of the matrix is same. Now, we come to an important definition which is right inverse. So, these definitions right inverse and left inverse are typically for rectangular matrices. In case of rectangular matrices, inverse of matrix really does not exist. Instead, what you say that there is something called right inverse of a matrix which is multiplied on the right side of the matrix and gives an identity matrix. C is right inverse of matrix A if AC is identity matrix I when A is a rectangular matrix with order m into n, that means A has m rows and n columns. Now, it is not guaranteed that right inverse will also exist, like if we take a square matrix, if the matrix is singular, then inverse of the matrix will not exist. Similarly, if we take a rectangular matrix, the right inverse may not exist, and similarly if we follow something like a Gauss elimination step, we will see 0 pivots and we will say that right inverse is not existing here. So, when the right inverse will exist, and it has a relation as evident from the title of this slide, it has a relation with existence of a solution. So, when should a right inverse exist? The right inverse exists if the matrix A has full row rank R is equal to m. The matrix A is of order of m into n. So, it has m rows and n columns, and all these m rows are independent. So, it has a full row rank, or the rank of the matrix or dimension of the row space is equal to m, and then only we will say right inverse will exist. That means, if we consider the matrices as collection of linear equations, we have all independent linear equations, and this is possible if number of column is greater than equal to number of rows, because if number of column is less than m, then we cannot have m number of independent rows. Maximum number of column is actually maximum number of independent columns. So, maximum number of independent columns will be the number of rows, number of independent rows. So, the rank will be n, which is less than m. So, n has to be greater than equal to m in order to have a full row rank matrix, and therefore, there are m before coming into this point we should write there are, if the matrix has a full row rank R, so it has R independent rows. That will imply what? Number of independent rows is equal to number of independent columns, sorry, not R, this is M. It has M independent rows. So, it has M independent columns. So, out of n columns, the matrix has n columns, out of n columns M are linearly independent, and column space is a subspace of R m. M is the number of rows. So, there are total m components in a column vector. So, column space is a subspace of R m. So, we have R m vectors as column vectors, and there are m independent vectors. Therefore, the entire R m can be spanned by few of the columns. So, we can say that there are m independent columns, which is the number of independent rows, they are same, and the columns of A span R m, because there are m independent columns, each column vector belongs to R m. So, there are total m vectors, independent vectors, which can form a basis of R m or can span the entire R m. So, few of the independent columns or m of this independence column will span the entire columns R m space. B, the right hand side vector, is a vector in R m. Therefore, B column space spans R m, B lies in R m, B must also lie in R m column space. So, if right inverse exists, if all the rows are independent, interestingly this is coming from the row perspective, if all the rows are independent, the column space is spanning entire R m, and therefore, B must lie on the column space. So, what we can tell is that A x is equal to B will have at least one solution for any B, because B is on the column space. It may have more than one solution, because there are more column space, the number of equations are less than the number of variables. There are more column vectors than the number of vectors in a basis. There are total n vectors, m are sufficient to span the space. So, there can be more than one solution, but there is at least one solution, because this ensures that B lie in the column space. Therefore, existence of right inverse ensures that the solution exists if right inverse exists or the rows are independent, and this is with the case that number of rows is less than equal to number of the columns. And we can say that this is due to the fact that columns span entire R m. So, this is from the comes due to the property of spanning of R m, that columns will span entire R m, B is a member of R m, therefore, B must lie in the column space. So, solution will exist when right inverse exists. Now, let us see what is left inverse. Left inverse gives uniqueness of the solution. Left inverse is it is B is, sorry, it is not right inverse, the term will be left inverse. B is left inverse of a matrix if B multiplied in the left of the matrix and gives an identity matrix, and if the matrix is of A is of the order m into n, then B multiplied before A gives us an identity matrix n into n. So, B will be n into m. So, both are rectangular matrices, left inverse and right inverse both are rectangular matrices in the cases when A is a rectangular matrix. And left inverse exists if the matrix A has full column rank or R is equal to n, which is possible similarly when number of rows is greater than equal to number of columns. Then we can have all columns independent, and number of independent column is equal to number of independent rows. So, we will also have n independent rows. So, what interestingly we have, there are n independent columns, and therefore, B vector can be expressed as only one linear combination of the columns of B, if B at all lies in column space. B may not lie in column space, because it does not ensure that the column space is spanning entire R m. However, the vectors in the in the matrix, the column vectors of the matrix, they are linearly independent. Therefore, there is at most there is only one linear combination of the column vectors which can form the vector B. This comes from the property of linear independence. So, Ax is equal to B will have at most one solution, and solution is unique if left inverse exists or the columns are independent with number of rows is greater than equal to number of columns. So, this comes from the uniqueness or and as well as left inverse comes from the property of independence, or I will write linear independence of columns. So, if the rows are linearly independent, all the rows are linearly independent, then we have right inverse which ensures existence of the solution. If all the columns are linearly independent, then we have left inverse which ensures uniqueness of the solution. So, let us move ahead, and we can check very easily that there are very simple formula for right inverse and left inverse. Left inverse is given as B is equal to A transpose A inverse into A transpose, and therefore, we can calculate it. Our idea is B A is equal to A transpose A inverse A transpose into A, which is identity matrix. Similarly, right inverse is given by the formula that C is equal to A transpose A transpose inverse. Left inverse, this also tells us one thing before coming into the next points, that A transpose A or A transpose is invertible. A may be a square matrix, A may have dependent rows or dependent columns. However, it may be not a square matrix, it may be a rectangular matrix, it may have dependent rows and dependent columns. However, A transpose A or A transpose can be invertible in the few cases. A transpose, this is invertible, A transpose is invertible when we have independent columns. Because this has to be invertible in order of existence of B or left inverse. So, if columns are independent, then A transpose A must be invertible. Similarly, A transpose is independent whenever we have independent rows. Go to the next point. Left or right inverse may exist even if the matrix is rectangular. Product of a matrix, and of course, for a square matrix they also exist, will come in a while. Product of a matrix and its transpose, which is A and A transpose, is invertible if the matrix has independent rows. And similarly, the vice versa is product of transpose and the original matrix is invertible when the columns are independent. This is a small piece of information which we should note here, and it will be important at later stage when we will look into more detail of independent rows and dependent columns, some square matrix of like that, some rectangular matrix like that. Now, we also should see what will happen for a square matrix. For a rectangular matrix, we can find out independent number of row less than equal to number of column less than equal to number of row. In both cases, all independent rows and all independent columns gives us respectively right inverse and left inverse, which is related with existence and uniqueness of the solution. Now, what will happen for a square matrix? This formula m less than equal to n, m greater than equal to n still holds, because equal to m is equal to n asserts that the matrix is square one. So, inverse of a matrix, for a square matrix inverse exists, inverse of a square always is for a square matrix, inverse of a matrix exists if right in and left inverse exist and they are the same. So, if both of them exist and both are same, both of them can only exist for square matrix, right, because m greater than equal to n is existence of left inverse, m less than equal to n is existence of right inverse. Only when m is equal to n we will have both the inverses exist, right and left, and then they are same, and then we will say that the matrix is a invertible square matrix. Inverse of the matrix, if inverse of the matrix exists, it has exactly one solution. Why? Inverse exists means that left inverse exists and left inverse exist means that there is solution exists, there is at least one solution. Similarly, right inverse exists for inverse both left and right exist. Right exists means there is at most one solution. So, when both the solutions exist, there has to be exactly one solution which satisfies at least one and at most one. So, if inverse of the matrix exists, and we have seen it in several cases, there is exactly one solution. However, the cases with rectangular matrices with left inverse existing, we can get at least, we should get at least one solution. We can, and we may get many solutions if the matrix is a rectangular one. Similarly, we can get at most one solution if right inverse exists, that means B vector will lie in the column space. So, we again further explored the idea of existence and uniqueness, especially existence of the solution, and we now look into the definitions we obtained in last few classes on the fundamental subspaces. There are 4 fundamental subspaces: column space, which is denoted by Ca, which is a dimension r, which is the number of independent columns as well as number of independent rows, and it is a subspace of Rm. M is the number of rows or m is the number of elements in one column vector. Null space of A has a dimension n minus r, and it is a subspace of Rn, where n is the number of rows and therefore, these are n is the number of columns, sorry, and therefore, these are the number of elements in one particular row vector. Row space of A is denoted by C of A transpose, or column space of A transpose has same dimension as column space, because number of independent columns is same as number of independent rows, and it is subspace of Rn. N is the number of components in row vector, which is equal to number of columns, and we have left null space or null space of A transpose. Sorry, this is not null space, we should write this is left null space of A or null space of A transpose. It has dimension m minus 1 and it is subspace of Rm. So, column space and left null space are both subspace of Rm, and null space and row space are both subspace of Rn. And number of independent columns is equal to number of independent rows, which is dimension of column space or row space. Dimension of row space plus dimension of null space is equal to number of columns, and dimension of column space and dimension of left null space is equal to number of rows. These are the few basic observations which we have made in last few classes. So, we will look into an example and see how null space, row space, column space, left null space look like for one particular matrix. And we purposefully choose one rectangular matrix because m and n will be different, and we can get different dimensions of null space and left null space also. Another interesting observation here was that dependent columns and rows introduce non-zero null space or left null space. So, if there is no dependent column, then the null space is a 0 vector. So, R is equal to m, and we will say that the, because dimension of row space and dimension of null space is equal to number of columns. If all the columns are independent, then dimension of row space, then dimension of row space, if all the columns are independent, then dimension of row space and dimension of the number of columns are same. So, null space is a 0 dimensional vector, which is basically a 0 vector, and same for left null space. So, dependent columns and rows introduce non-zero null space and left null space vectors. Now, we will take as an example, we will take an rectangular matrix which has dependent columns and rows, so that we get non-zero null space, left null space, and let us see how do they look like. So, let us consider the matrix A, which is a m is equal to 4 and n is equal to 3. I have written it wrong, I should correct it, which is a rectangular matrix with m is equal to number of row is equal to 4 and number of column is equal to 3, 4 into 3 matrix. Okay. Now, what are the column space vectors? Are basically the columns, and which is 1 2 0 1, 1 0 1 0, 2 2 1 1. Now, if we look into the column space vectors, the third column space vector is summation of first two column space vectors, because I said purposefully I have chosen a matrix which has dependent columns or rows. So, what we get? We get that the third column is summation of first two columns. Therefore, there are two independent columns, R is equal to 2. So, rank of the column space, rank of the column rank of the matrix is 2, rank of the matrix is 2, dimension of the column space is 2, because there are two independent columns. Therefore, we should be dimension of the row space also, but let us look into the row space. And the row space vectors are 1 1 2 2 0 2 0 1 1 1 0 1, they are written in this transpose form as following. And then what we can see is that fourth row, this is the fourth row, this is multiple of fourth row is multiple of second row, fourth row is basically half of second row, and third row is first row minus fourth row. So, fourth row and third row are dependent on first and second rows. So, there are two independent rows, and number of independent rows is equal to number of independent columns, that is also verified here. Now, we will look into the null space. So, before that, column space is given as linear combination of the two independent columns. So, any column space vector will have any column space vector, any vector which lies on column space will have this form. What is the form? Alpha is an arbitrary constant multiplied with one column vector plus beta another arbitrary constant multiplied with other column vector, and they can constitute any vector which is lying in the column space by choosing different values of alpha and beta. So, there can be infinite vectors in column space. It is two vectors. So, in R4, because they have 4 components, in an R4 they will construct a plane. We cannot visualize what is a plane in R4, but they will construct a plane in R4. What is further important is that if we choose alpha is equal to 0 and beta is equal to 0, it is a 0 vector. 0 vector is always a member of any vector space, so it lies in the column space. And the row space will similarly look like the transpose of the row space, column space of A transpose is some constant gamma into 1 1 2 plus some constant eta into 202, and we can really form any vector in row space will have this form. So, we can really construct the plane in 3D by say 202, right. So, one vector will be this is x y z. So, 202 one vector will be something like this, and another vector will be x1 y1 and z2. There will be another vector like this, and the plane contained by this vector, any vector in this plane. So, this has to be extended like this, any vector in this plane will be a row space vector. So, if I draw anything like this will belong to row space. So, this will be the row space which is a plane in a 3-dimensional geometry. However, so we will now look into the null space, and let us solve the null space equation, which is Ax is equal to 0, and get null space as 1 1 minus 1 and one null space vector that. So, if any null space vector will be constant multiplied with 1 1 minus 1. So, this will be basically if I have if I have the axis x y z, this is basically 1 1 minus 1. So, 1 1 and minus 1. So, this is basically some line like this which passes to 0, and any vector along this line will be the null space vector. So, null space is a line passing through origin and 1 1 minus 1. Similarly, the left null space equation A transpose y is equal to 0, and solving we get two vectors for left null space, and any vector in left null space is a linear combination of these two vectors. So, this is also, because there are two vectors, this is also a plane in R2, R4, this is a plane in R4. So, left null space is a plane passing which contains the vectors 1 0 0 2 and 1 0 0 minus 2 and minus 1 0 1 1, it is again a plane. So, that is how we can find out all the spaces, null, row space, column space, left null space, and check their dimension should come accordingly. If we only have to find out the number of independent columns and rows, and that will give dimension of row space, column space. We have to subtract that from number of columns and number of rows to get respectively the dimension of left null space and left null space. So, we get row space which is this, which has dimension 2, null space which has dimension 1, all they are membered in R1, all there are 3 because they have 3 components in each of the vector. Now, row space is a plane containing the vectors 1 1 2 and 2 0 2 in R3. Null space is a line joining origin 1 1 and minus 1 in R3. And if we take dot product between the vector, any vector in null space which is which will have this particular form, with any of the row space vector which will have this particular form, and this dot product will be, we can do it, this will give us 0. And two vectors. So, dot product between two vector is 0, that ensure that if A dot B is equal to 0, this ensures that A and B are perpendicular. So, what we are getting here, at least for this particular example, a row space vector, a general form of a row space vector, is perpendicular to another general form of null space vector. So, every row space vector is perpendicular to any of the null space vectors. Same observation, there is an interesting observation, a property of the vector subspaces will follow later. This the same so this what we can say, relation between row space and null space, dot product between a vector in null space and a vector in row space is 0. So, any null space vector is orthogonal to row space vectors, both are vectors in R3. So, we can write null space is orthogonal to row space. That means, the null space is a line, null space is a line and row space is a plane. So, this is row space and this is null space is orthogonal to row space, and that is why we can have any vector in row space and they are joined at origin, any vector in row space perpendicular to any vector in null space. At least this is true for this particular example, that null space is orthogonal to row space. Similarly, we can look into column space and null space and left null space and say that any vector in left null space has a 0 dot product with a column space vector, whereas both are vectors in R4. So, in R4 the left null space is orthogonal to column space. And one interesting thing comes out of the second observation, that left null space is orthogonal to column space. So, we look into solvability of Ax is equal to b. So, for example, this is the left null space and this is orthogonal to column space. So, if we have any vector b, say this is a vector b and it has some component along the left null space, this is the, it has some component along the left null space BL. Therefore, the component along the left null space is always orthogonal to the column space. So, B has a component which is away from the column space, therefore, B is not on the column space. So, X is equal to B will have no solution. B may have some component, say B C along column space and right B L along left null space, but if any vector B has some component along left null space is orthogonal to column space. Therefore, B will have some component which is not on the column space. B will have a component orthogonal to column space. B will, so if this is the column space, B will come out of the column space because B will have a component orthogonal to the column space. Therefore, B is not on the column space and X is equal to B does not have a solution. So, this is a very important observation, that right hand side vector B, if it has some component along left null space, it does not belong to column space and X is equal to B has no solution. So, this is one important observation, but this is made on this particular example which we have chosen in this case. In next class, we will look for more general expressions and see what happens for a general matrix, what is its left null space, column space or null space, row space relation, and how are they important in case of solution of X is equal to B. Thank you.